Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing the probabilistic method. So again, to remind you from last class what the probabilistic method is, at its root it is the use of randomness to prove the existence of combinatorial objects. Today we'll be discussing yet more standard classical examples of the use of the method. In particular, we will be discussing property B, which is also known as hypergraph 2 coloring, KL systems, and sum-free subsets of integers. So again, this is just a number of examples showcasing the method at its heart in its somewhat more basic form, some of the intricacies and nuances involved with it that we learn best by practice and experience. So here is our first example of the day. It's about hypergraphs. So to remind you, a hypergraph is a pair H equal VE, where V is a finite set of vertices, and E is a family of subset of V called edges. So this is like a graph, except the edges are allowed to be more than just pairs of vertices. They may be any sets. A hypergraph is n-uniform if every edge has size n, so all the edges are of the same size. Thus, a graph is a 2-uniform hypergraph. And then we say that a hypergraph H has property B, aka also known as 2-colorable, if there is a 2-coloring of V such that no edge is monochromatic. So what does that mean? That you can actually, for hypergraphs, when we do coloring to make it different from just as you might do for graphs, we only require that there are no monochromatic edges. So if we have 3 or more vertices, as long as 2 of them receive different colors, then this is what we mean by coloring. And so this is how we define coloring for hypergraphs. This particular idea of 2-coloring, somewhat analogous to bipartite, therefore, for graphs, was called property B historically. And then the question of interest is, let M of n denote the minimum number of edges in an n-uniform hypergraph that does not have property B. So an interesting question is, how few edges do we need to actually get a non-2-colorable hypergraph? So this attracted a lot of attention back in the day. There's a nice lower bound by Erdos from 1963 that proves that M of n is at least 2 to the n minus 1. Right. So again, this doesn't say a lot for a particular uniformity. So for example, for graphs, when n is 2, this just says that you need at least 2 edges, which is not that interesting, but the dependence on n here is the interesting part. So let's prove this, actually. This is a nice small example using the probabilistic method. The proof idea is what? So maybe again, pause and think for a moment, what would you do now that you've seen some examples of the probabilistic method? So the idea is to take a random 2-coloring, right? So here we need to show that we can color any such hypergraph with few edges. So let's do this by taking a random 2-coloring. So let's go through the proof. The probability space will be a random 2-coloring of H, where each edge is independently colored red or blue with equal probability half and half. And then what are our events? Well, we want to hope that this avoids monochromatic edges. That's really a proper 2-coloring. So for every edge E in the hypergraph, we'll let A be the event that E is monochromatic. Again, that's our bad event. So this is our standard. We make a probability space, we take a series of bad events, and we show that none of them happen. Proof. So let's do that. So we need to calculate the probability of AE. What is that? Well, there are 2 colors, so you could choose one of the 2 colors, and then you would need that edge is, every vertex, in the edge is actually colored that color. So product over the vertices in the edge of a half, which would be 1 over 2 to the n, where n is the uniformity, times by 2 gets you 2 to the 1 minus n. So that's the probability that an edge is monochromatic. And then by the union bound, we know that the probability of the union of these events is at most their sum, which is the same for every edge. So it's e of h times 2 to the 1 minus n. So the number of edges times 2 to the 1 minus n. Since the number of edges is assumed to be smaller than 2 to the n minus 1, that whole sum is less than 1, which means that with positive probability none of the events occur, that is, that there exists a 2-coloring of H without a monochromatic edge as desired. So you can see easily where the number of edges played a role. We just calculated a probability and did a union bound, and it worked out. But now let's talk about upper bounds. Amazingly, Ocean the same year showed that m of n is somewhat roughly on the same order, that it's almost 1 plus the low 1 ELN2 over 4, that's just a constant, times n squared times 2 to the n. So we had a lower bound of roughly, 2 to the n, rather 2 to the n minus 1. Here we have roughly that, but now times some factor of n squared out front. And let's prove this. What will be the idea? What is the proof idea? So maybe again, pause the video and think, how would you apply randomness here, right? So before we needed to produce coloring, here we needed to produce a graph that's not too colorable on this number of edges. How might we invoke randomness there? So the idea is to take a random n-uniform hypergraph on an appropriate number of vertices and edges. So we'll get into that, but to take a random one. So this is a bit of the slippery part. How do we actually make this randomness work? Well, we will choose a number of vertices. So we'll let v be a set on little v, that's going to be equal to n squared over 2 elements. So we're going to restrict ourselves to doing randomness only on a certain number of vertices. All right, so that's going to be part of the proof. So figuring out actually what that correct number is to make this all work is quite important. And here it's n squared over 2, but again, as we saw last time, this is somewhat retroactively chosen to be optimal. So just think for the moment that v is arbitrary, and we will later try to pick the correct v to minimize this bound m of n. So then now that we've done that, we will actually choose it to be random and kind of uniform there. So we won't do any activation type probabilities. Instead, what we're going to do is we're going to choose S1 up to Sm, each independently and uniformly among the n sets of V. So this will be our probability space. So we're going to choose our m edges to be, of course, of size n, that's n uniform, and then to be from this set of elements. And what it's precisely do I mean by this, independently and uniformly? So it's not exactly maybe clear if you're not used to this. So let's go through that. So here, what I mean is that we are choosing with replacement. So the SI might not be distinct. So for each SI, you choose it at random from all the n sets. So you may end up with the same n set more than once. So this is known as with replacement. So we're choosing elements from a set. So here it's subsets from this family of all subsets, but we may be allowed to pick the same one more than once. That's called with replacement. And thus our hypergraph may end up with fewer than m edges, because we can't, a hypergraph, we're not doing multi-hypergraphs. You can't take an edge more than once. So really we just simplify it down, taking one for each set chosen more than once. But that's actually fine for our problem, because if we can show that that hypergraph is still not too colorable, even if it has multiple edges, which don't matter for coloring, then it has at most m of n edges. And so it will have at most the number that we have. So if it ends up with fewer, that's fine for our problem. So that's going to be the easier way to implement this. There is an alternate way to do it, which is without replacement. So that's equivalent to saying that uniformly you choose a set of m distinct, keyword on distinct there, n sets. And you do this uniformly at random among all such choices. So among all the Vn choose n sets of V, we choose a set of m of them at random. And that could work too as well, and we'll point out in the proof where this alternate version you would do that. The issue is there the analysis is slightly harder. Now, if that is what we in fact required, then we would do it that way. Here, since we're happy with fewer edges in the outcome, we'll do it with replacement instead. So get used to these terms, so they show up when you're doing certain random experiments with balls and bins and such, with replacement, without replacement. All right, then let's proceed. So now we've said how we're going to construct a random hypergraph. Now we have to do the coloring. So now we have to talk about coloring. So let chi be a two-color in a V with A red vertices and B blue vertices. So here's the important point. We have red color and blue color, say, and a coloring will have some number of red vertices and blue vertices. So let's just fix the number here. Clearly B is going to be equal to V minus A. And now what are we after is what's the probability that SI is monochromatic under chi? Right, so what are we aiming for? So we want to be able to show that in our random hypergraph, all of the colorings fail. That means for some SI, they are monochromatic. So let's look at an individual coloring chi and an individual subset SI. And what is its probability? Well, I claim it's A choose n plus B choose n divided by V choose n. Why is that? Well, there's V choose n possible n sets of V elements. And then what are the monochromatic options? Well, if I have A red vertices, there's A choose n subsets that are red, and then there's B choose n subsets that are blue. These are the only options that get you monochromatic, so we sum them. Now that's a little bit unwieldy to use. We're going to create a uniform lower bound by noting that y choose n, this binomial, is convex in the variable y, which then in turn means that the expression above is minimized when A equals B, just by the definition of convexity. So what does that mean? That means that the smallest such probability is actually 2 times V over 2 choose n divided by V choose n. And that's a little bit of a lie because we need to assume that V is even. Since we're only really doing asymptotics, it won't change too much to do that instead. So then let's just make that assumption. Then the minimum would be when A and B are both V over 2. So the probability that SI is monochromatic under chi, and here doesn't matter, there's no A and B anymore, so I can just say this works for any chi, coloring chi, is at least P, which is this, we're going to define to be this number. Now, what do we do? Well, now that we've calculated that first bit of probability, we can actually proceed with the events. So again, for every 2 coloring chi of V, we're going to let A sub chi denote the event that none of the SI is monochromatic under chi. That is, that A chi is actually a proper 2 coloring. So these are the things we want to avoid, these bad events, right? We want to have our random hypergraph not actually be a proper 2 coloring for any chi. So we take it, the events, the randomness is in the edges, and now the events are based on the colorings, which is the flip of our lower bound one where the randomness was in the coloring and the events were for the edges. Okay, so now we can actually proceed to calculate the probability of A chi, and here's where replacement is useful. Since the SI are chosen independently, the same one may be chosen repeatedly, you can see that then the probability that A chi is just 1 minus P to the M. Right, so P was our probability to be monochromatic, and 1 minus P we want to avoid. We want to avoid the thing, so we take the product over all of the M's. So that would give us this. It's exactly equal to 1 minus P to the M. So here I'll note that if you've chosen it without replacement, if we did it again without replacement, so you had to take distinct sets. What we would do differently in the proof, it's not too hard, it works for us here, is that we would instead upper bound. So we'd say that the probability A chi is at most 1 minus B to the M, by noting that choosing non-monochromatic edges, right? So for a fixed coloring, there are just edges which are monochromatic and ones which are not. So then if you're doing it without replacement, choosing non-monochromatic edges is more unlikely without replacement, right? So if I have to choose M non-monochromatic edges and I'm not allowed to put them back, it's going to be less and less likely to pick non-monochromatic edges. So actually you could give an upper bound, which is what we need for our next bit, because either way we're going to use the union bound. Again, that the probability of the union of these bad events is at most their sum. They're all the same if you use replacement, or upper bound it if you do not by 1 minus P to the M. And how many colorings are there? There are 2 to the V number of colorings. For each vertex, you pick a color. So there are 2 choices, so you get 2 to the V. And then the claim is that this is less than 1. If we did everything correctly, if we picked M correctly and P and V, then this will be less than 1, because then with positive probability none of the bad events happen, hence there exists a choice of these SI, which therefore gives a hypergraph H on at most M edges, such that every 2 coloring of H has a monochromatic edge. That is, it's not in fact 2 colorable. And that will conclude the proof. So here though, let me now turn to actually this inequality. So what v and p, p we've defined because we took the minimum there, but what v should we choose, what m do we end up getting, how do we do that part of the analysis? So let's look more closely at these asymptotic details. So again, we need to show that 2 to the v times 1 minus p to the n is at most 1. We can upper bound that by using that 1 minus p is at most e to the minus p. So we will upper bound that by 2 to the v e to the minus pm. And hence, if you look at that, when is it going to be less than 1? It's going to be less than 1 when m is larger than v ln 2 over p. So that's what we need to know, that m is bigger than that number. So we needed to discuss, about the choice of v and m. So how would this go about? Well, to guarantee our choice of m works, so we've kind of locked in our choice, we then need to know that v ln 2 over p is actually smaller than m, so we need a reliable upper bound on v ln 2 over p, and thus we'd actually need to know a lower bound on p. So we're interested in this p, but we need to actually figure out a lower bound. So from the book, it's not so clear that this is how it's working, but this is how it actually works. And so here again is our p. It's 2 times v over 2 choose n over v choose n. That can just be rewritten, so you can cancel the n factorials. You can divide through with 2, so you get 2 to the 1 minus n times this product of v minus I over v minus 2i. And it can be shown that that's approximately 2 to the 1 minus n e to the minus n squared over 2v. So you can see that because that's the terms there are roughly something along the order of 1 minus I over v, because again, I is the most n, it's much smaller than v, which is n squared over 2. So it's roughly 1 minus I over v, which is roughly e to the minus I over v, which will get summed up. If you sum up i's from 1 to n, you get roughly n squared over 2. And so you get roughly that number. But again, this is only an approximation. A pretty good one, but an approximation. So I'll note what you really need to do here is a more careful lower bound analysis with error terms. So this is somewhat annoying, right? That we'd actually have to argue what you'd actually getting 1 minus I over something v minus 2i. So then we need to expand that out more in a Taylor series and get a good bound with the terms. And then we're actually, again, lower bounding, so we can't just use that 1 minus p as a most e to the minus p. We need to use a more complicated inequality in the other direction. And we'll have to put all of that together. So you'll end up with some error term, but it's going to be a lower order, especially for our choice of v. Now, how do we actually choose v then, if you believe in this approximation? Well, the calculus, elementary calculus derivatives show that v ln 2 over p, which is our m, that's the thing we're taking as the lower bound for m, the thing we're trying to minimize. Well, that, if you plug in, is approximately 2 to the n minus 1 ln 2 times v times e to the n squared over 2v, as the exponent gets flipped. And this is minimized when v is equal to n squared over 2. That you could just see from the last line. If you take calculus and you say set n squared over 2 to v to be kind of your variable x, then really they're up to a constant. We're taking the derivative of e to the x over x, which is equal to e to the x 1 over x minus 1 over x squared, which is indeed 0 when x is equal to 1. So that would mean when n squared over 2v is 1, that is when v is n squared over 2. And you can check that that's indeed a minimum if you wanted to do second derivatives or plot it and such. But that's how, again, you'd find it. So that minimum analysis, to repeat, does not need to be part of the proof. It's just trying to optimize our bounds. But if you're just trying for any bound, just picking v is fine. However, the part about approximating p and finding a lower bound is actually necessary in essential proof. So what I gave on the previous page, or even here, does not complete a proof of this statement. You really have to, for the sake of the proof, we actually have to know that m is greater than v ln 2 over p, which is not at all clear from what I've shown here, except to say approximately it should be true, but really you want to do this lower bound analysis. So that shows you some of the difficulties in using asymptotics, that maybe the bounds aren't quite the way you want to go, and you might have to invest more effort in getting them to work. All right, so that concludes our hardest example of the day, was this upper bound, but again, a very classical property B, this two-color hypergraphs, old results. But I wanted to turn to a combinatorial result that's of a different flavor. It's not. It's about bounds, but it's more structural, it seems, in some sense. But we're going to do a probabilistic proof about it. So here's the idea. A family F is called a KL system. So here it's pairs of sets AI, BI, I equal 1 to H. So you can think of this, again, as some kind of set system or equivalently hypergraph. If the AI will be of size K, the BI will be of size L. So kind of we have K sets and we have L sets, so it's a KL system. We're also going to require that AI is disjoint from BI, that their intersection is empty. So we have these pairs that are disjoint, and yet the cross pairs, AI intersect BJ, is non-empty for every distinct I and J. So it's kind of this nice system where you have pairs of K sets and L sets. The pairs themselves are disjoint, but all the cross pairs are actually intersect. And the amazing thing about this is the following theorem, that if F is a KL system, then that number of such pairs is actually upper bounded by a function of just K and L, namely K plus L choose K. So this property about the cross intersecting, in addition to the being disjoint in the individual pairs, is enough to provide, to force a bound. You can't have an arbitrarily large such system. Again, with simple systems, not allowing the same element many times. Though that would also then intersect, actually, so that might be fine. So how would we do this? Now, what's the proof idea? So I want to make you stop and pause for this one, because it's actually, this is maybe why we're doing it, it's nice that it's different from what we've seen before. So, because what are we aiming to? We need to prove an upper bound, right, on the number of edges. So we're not trying to construct a coloring, we're not trying to construct a system at random or anything. No, we're given the system and we need to prove some bound. But what we're going to do is we're going to take a random ordering of the elements. So these system lives in some set of elements, some larger hypergraph, if you would. We're going to take a random ordering of those vertices, and we're going to use probability to upper bound the number of edges. So we're going to use probability and say, given these properties about the system, actually, then knowing what we know about probability, there just can't be too many edges. So it's quite an amazing proof in that regard, even though it is quite simple. It's a different take on the probabilistic method. So let's see this in action. So what's going to be a probability space? As promised, we're going to take a random ordering of all of the vertices. So here, the union of the I equal 1 to H of AI union BI. Anything that's not in any of the AI or BI, I could just delete. They don't matter. So we're going to take a random ordering of all the vertices that do matter. And what do I mean by random ordering? I.e., each permutation will be equally likely. So that is our probability space. Now we need events. So again, we'll set it up with events for every I in H. Here's the idea of the event. We're going to let xi be the event that all elements of AI precede all elements of bi in the ordering. Right? So the AI and bi for a given I were disjoint. So what's the chance that all the AIs appear before all of the BIs? It's a well-defined event that we can calculate the probability of. And here's the probability of xi. It is 1 over k plus L, choose k. So why is that? Well, forget about all the other vertices that are in AI and BI. They don't matter where you put them in the ordering. So what really matters are what's the ordering on these k plus L elements of AI union BI. And now, given that, well, what are the possible ways to do this? Well, we need that of the k plus L factorial such orderings, we need all the AI first, we need all the BI second. There are k factorial orderings of the AI and L factorial of the BI, so then if you do out the arithmetic, you get this number. So that one's easy to calculate. And then here's the key claim, is that the xi are pairwise disjoint. So why is this? So maybe if you want to stop the video and prove this to yourself, you could go ahead. I'll give you the short, nice proof, but it's going to take on to the next slide as well. So suppose not, that is, there exists an ordering where AI precedes BI and AJ precedes BJ. So, right, there would be some XI and XJ that would intersect. So what would it mean? So we have AI precedes BI and AJ precedes BJ. And now, without loss of generality, the last element of AI, say, precedes the last element of AJ in the order. So somehow we either see all of the AI first or all of the AJ. They can intermix each other, don't get me wrong, just which one do we see all of first? So let's say that's AI. Well, then what happens? Well, if we see all of AI first, we haven't seen the last part of AJ, then we see that, well, then we haven't even seen any of the BJ. So that means that AI precedes, all of AI precedes all of BJ, contradicting that AI intersect BJ is non-empty. And that concludes the proof that these events are disjoint. Why is that good? Well, using disjointness, we know that the probability of the union of all events, that's an event itself, is at most 1, that's by probability. But then disjointness says that that union must actually be equal to the sum of all these probabilities. We calculated all of them, they were all the same, they were all k plus L choose k. And how many events are there? There are h in that sum, so you get h over kl plus k. So if you rewrite that inequality, you find that h is at most k plus L choose k as desired, completing the proof. So here it was a bit strange. We used randomness, we took a random ordering, and we did events, but we did all that to show, to derive this bound from the properties from the graph. Not trying to build a random one, using the randomness to actually give insight into the number of edges actually possible. So in our last, I did want to remark though that the theorem is tight. So nice part about this, unlike some of the previous examples where we're just kind of giving somewhat matching lower and upper bounds, here it's obvious it's tight because if you just take 1 up to k plus L as the vertices, and you take all such disjoint pairs. You take every set A that has size k, and then the other L elements, they will form pairs that don't intersect each other, but cross-intersect all the pairs, and then that indeed has k plus L choose k pairs. So remarkable, we use probability to prove a matching upper bound to this straightforward construction. Now our last example of the day is about sum-free sets. So far we've looked at graph theory. Today we did more about hypergraphs and set systems, so combinatorics more generally. Now we're going to do a bit of number theory actually, combinatorial number theory, because probability can also apply very well there. So here's something quite natural. A subset A of an abelian group G is said to be sum-free if there are no A1, A2, A3 in A, such that A1 plus A2 is equal to A3. So a subset is sum-free if no element is the sum of 2 other elements. And here's a remarkable theorem of Erdos from 1965 that says for every set B, B1 up to Bn, of n non-zero integers, that contains a sum-free subset A of size strictly greater, actually, than a third of n. So that's quite a remarkable theorem. How will we go about doing this, right? So we're just given non-zero integers, and we want to show that they actually have a decent sized sum-free set. So let's think about the proof idea. Now this, again, maybe I won't have you pause, as it's a bit hard to see. What would you do with this? Where does this 1/3 come from? How would you use randomness here? But that's why we're doing it. It's a remarkable example, basic though it is. So how does it work? We're going to use a random multiplication and then take it mod p. So we have this set of integers, and you think there's no structure there, right? But actually there is structure. So what we can do is we can take this random set of integers and we can embed them in a larger, mod p, prime space, and we can kind of take a random multiplication of them to shift this set of integers, and wonder what happens across all of these shifts. So if we kind of do this at random and claim that there is at least one shift that will land with a lot of its vertices, a lot of its elements on a sum-free subset, showing that the original one was actually sum-free. So let's go through this. So here's what we're going to do. We're going to let P be 3k plus 2. That's going to be a prime. So a prime of the form 3k plus 2, such exist. And we're going to choose it to be very large, so it's going to be much larger than twice the max of any of these integers. So if they're only finite, there's infinite primes, this will work out. And now what do? We're going to let C be the set k plus 1 up to 2k plus 1. So it's kind of the middle third of the integers up to P. So we have this kind of middle third set C. And now we'll note that C is actually a sum-free subset of the cyclic group ZP. Why is that? Because if you add any of them, then you kind of get back around. Either the sum will end up between 2k plus 2 and 4k plus 2, which will be k mod p, and so it won't end up back in the middle. So this middle is a nice large sum-free chunk of ZP. And we'll also note that C over P minus 1 is equal to K plus 1 over 3K plus 1, which is strictly greater than a third, therefore. So it's a chunk that's larger. It's about almost at least a third of our set. And now of the set P. Now what we're going to do is as our probability space, we're going to pick an integer, a random integer chosen uniformly in 1 up to P minus 1. So let X be this. So here's the idea. We're going to do this random multiplication. So we're going to define di to be xbi. Again, take in mod p. So we're in the cyclic group. Do that for each of the bi's. So we think of our bi's as somehow living in a larger kind of space, and we take a random multiplication of it. And now what does that do? That will end up behaving quite nicely, because in particular that means the probability that di is in C is equal to C over P minus 1, which is strictly greater than a third. So why is that in this cyclic group, this prime space, when we're multiplying, it will just permute this X will just permute all of the integers around. So there is always one X that will get you from bi to any other integer 1 up to P minus 1 in this multiplicative type group. So that's actually good. That means that what's the chance it ends up there? Basically, there is a set of exactly C integers, CX's for each bi, that will get you into C. So it'll be C over P minus 1. So that's where that number comes from, just basic number theory. And now we're almost done, because now we're going to let A be the I in N where di is in C. So we're going to pull back. So we ended up some of them ended up in the sum-free set. We're going to pull back that set to the original elements coming from this B. And by linearity of expectation, we know that the expected size of A is the sum over the I and N of the probability of di in C. And what were those? Those were at least strictly greater than thirds, so this sum is strictly greater than N over 3. So therefore, we expect, so this is the idea, we know that there's this chunk of a size of third. We do a random multiplication, so probability will work nicely there. In expectation, then, at least a third of the integers will end up in the sum-free set. We claim the pullback is going to also be sum-free. So let's go through this. Again, this is just expectation, but that means there is a choice of X where A is at least N over 3. And now I claim that A is a sum-free subset of B, since if actually A1 plus A2 was equal to A3 for some choice of A1, A2, A3 in A, then what would that mean? Well, that would mean that X times A1 plus X times A2 would equal X times A3, and those would still be equal if you mod them by P, and hence those numbers are D1 plus D2 would equal D3 mod P, but that would be a contradiction, since then D1, D2, D3 are in C by assumption, and C is sum-free, as we've already shown. So that concludes this number theoretic proof. That concludes our basic examples for this time. And so today we've seen about hypergraphs, about two-coloring there with KL systems, and here a taste of using probability, the probabilistic method, and combinatorial number theory, lots of different ways of using the method. So I hope you enjoyed all that. Until next time, see you then.